In this lecture, we're going to rederive the geodesic equation using a physical argument instead of a purely mathematical one. The purely mathematical one is actually my favorite, but this one shows up in so many books that we just can't ignore it, and if I'm claiming that we're designing these lectures to make reading books a little bit easier, or take the edge off of the different presentations and approaches, we really do have to cover it. It's also physics, so we should understand the physical argument. The core of mathematics of the physical argument is the calculus of variations, and that is a starting point that almost every GR book assumes that the reader has, and indeed we're going to assume it too. I'll just give a rough outline in a moment about what I'm assuming every viewer of this presentation is already aware of. But there's some disadvantages to the calculus of variations approach that just take time and detail to overcome, and we'll go through all of those. This may take 2 lectures. Now, the principle of least action is a very deep subject, and the following things should be familiar to. The first thing is that the action itself is an integral, where in the classical physics, you're integrating with respect to time. Time is the unique parameter, is the ultimate independent variable for the whole shebang. The Lagrangian, as we'll show, has a bunch of generalized coordinates, but then at the end, it's always dependent on time. So you're trying to minimize this integral, which is called the action, and hence the principle of least action. In the integrand of the integral is the Lagrangian, which in classical physics is defined as the difference between the kinetic and the potential energy when evaluated in some inertial frame of reference. And all of these things, if you've done these problems, you should know what that means. You take a problem, you usually write down, you figure out, well, ultimately, you start with figuring out the coordinate system you're going to work with. And in that sense, you end up looking for these generalized coordinates and their first derivatives. And once you construct those coordinates, for like a double pendulum, they're frequently angles off of the vertical and the speed, a rate of change of those angles, for example. When you construct those coordinates and you construct this Lagrangian, when you construct those coordinates, you build the kinetic energy, you build the potential energy, you take their difference, that's the Lagrangian, that's what ends up being the integrand of your least action integral. And all that should make perfect sense to you, or this lecture is really kind of a loss. Now, what's interesting is what we're going to do is we're going to work with a calculus of variations approach. We're not literally going to construct a Lagrangian, however, but we are going to ultimately exploit the key result of the basic premise of the principle of least action, and that's the how do you determine what this minimal path is, and that is through a differential equation called the Euler-Lagrange equation. And this is the Euler-Lagrange equation. This guy here should really be what is really familiar to you, because the typical problems in classical mechanics, which I presume you have done at some point, even engineers sometimes do this work. This is ultimately introduced in mechanical engineering quite a bit. But you calculate the Lagrangian, and once you have that thing, you create this equation for each coordinate, for each of the n different coordinates. Presumably, you create n generalized coordinates, and you can produce this Lagrangian for these n generalized coordinates. And oops, the way I should draw this with a t here. Then you take this derivative you take the derivative of the Lagrangian with respect to the generalized coordinates. You take the derivative of the Lagrangian with respect to those generalized momenta. These guys were called generalized momenta. These guys were called generalized coordinates. Then you take the derivative with respect to the ultimate independent variable, which is usually time. It won't be time in our case necessarily, but it's usually time. The difference between those two should be 0. So that's a differential equation, right? That's a differential equation, and there will be I or n differential equations that all have to be simultaneously satisfied. And then once you've done that, it's a differential equation for, it's going to be ultimately a differential equation for these q's, right? And the q dots, and that's your answer, right? Your answer is, what is the value of qi with respect to time? At any point you give me the time, I'll tell you the value of the ith generalized coordinate, and I'll tell you the value of the ith generalized momentum if you give me the time. So everything is going to be ultimately a function of time. So that's the whole point of the Lagrangian mechanics. It's a very deep subject. There's a lot of really cool problems. I started really liking mechanics when I first was diving into this, because you were doing really interesting problems now. You were trying to understand, the double pendulum I remember being really excited by the double pendulum. You have a pendulum that's swinging, and then on the end of the pendulum is another pendulum, right? And you could do a triple pendulum, a quadruple pendulum, it doesn't really matter. You could add as many pendulums as you wanted, and I thought that was really a breakthrough in how valuable things were. Instead of sticking down, okay, there's a force going this way, and then a force of gravity, and then a force here, and trying to walk through this using just standard sort of engineering, block and pulley sort of physics. This was really a much deeper thing, and it was a big eye opener for me. Anyway, that is ultimately the core mathematics we're going to start. What you need to be comfortable with in order to proceed is this here. We're actually not going to create a Lagrangian necessarily, not in this classic form. What we are going to say is that geodesic paths minimize the proper length of the paths through space-time. And the length of a path through space-time is an integral over a parameter of an integrand. And that integrand is going to take the place of L, and then we're still going to use the Euler-Lagrange equation to find that minimum path. Okay, so let's begin. So we begin with our fundamental idea of a small increment of path length in general relativity. We know we have a metric in our four-dimensional manifold. That's an established idea. And we have a curve. And the way the mathematics is almost always written in most of the books I've examined, if not every single one, is that the curve is given by the parameterized function x mu of some parameter. Lambda is what we'll use. So our parameter will be lambda. But this is the curve in space-time. So that really is nothing different than the way we've been doing things before. Here we have lambda along this little real axis of just a real number lambda, and then the map into space-time is given by x mu of lambda. Sometimes this confuses people when you've been working in the more abstract and strictly mathematical versions of relativity, because you understand the x mu should be a coordinate function, and this map should be called something else. And we've done that before, right? We've called this map gamma of lambda, and then the actual, say, I coordinate, or say the 0th coordinate of the point at gamma sub lambda would be x0 gamma sub lambda, right? And this is the coordinate function that just pulls out the first coordinate of this guy. And x, actually, that would be perhaps x mu. So that would be the function x0 acting on gamma mu of lambda, which is the same as x0 acting on gamma 0, gamma 1, gamma 2, gamma 3, where all of those are really gamma 0 of lambda, right? And then this equals gamma 0 of lambda, right? So this pulls out. That's one of the ways we usually think of this in terms of if the function is named after the coordinate system, we call it a coordinate function, and it just pulls out the appropriate coordinate. But that's not how, in the shorthand version of things, that's not how it's done, right? That's not how it's done. The actual curve itself is just, it's all shortcutted, right? The actual curve itself is called x mu of lambda. And so this point here is simply x0 of lambda, x1 of lambda, x2 of lambda, and x3 of lambda, all bundled together as a quadruple pair, or a quadruple of points. And then, of course, this other point further up the road would just be x0 of, say some other value of lambda. We'll call it lambda sub 2. A lot of subscripts and stuff here, so et cetera, et cetera. So that is the curve construction that we're dealing with. So because of this, when we look at these two terms, what are we really thinking of? We're really thinking, well, we've got x alpha, which is a function of lambda, and we have the derivative of that with respect to lambda, and we very frequently just write that as x dot alpha, where we understand that the dot, this dot here, is simply an indication of this thing here. So in a lot of our work, we're going to write down the square root of g alpha beta x dot alpha x dot beta, because it's just a little bit cleaner, right? And, oh, there's a minus sign here. So then but about that minus sign, we have to talk about this thing here. Well, we know that g alpha beta is just shorthand for g alpha beta, which is a function of space-time, which we usually just throw in with an x, but I could put it with an x and some other subscript, say mu. So I know that g alpha beta is a function of space-time alone. And we also know that if we're using the convention -1, 1, 1, 1, that is our rectilinear Minkowski metric, or the Minkowski metric in Cartesian spacetime. So if the local spacetime in free fall has this metric, as opposed to 1, -1, -1, -1, but if it has this guy here, we know that time-like paths will have lengths that are less than 0. Right? So time-like paths have lengths that are less than 0, space-like paths have lengths that are greater than 0, and null paths have lengths that are equal to 0. So with that in mind, we know that this product for any time-like path will be less than 0. So we have to throw a negative sign there so the square root makes sense, right? So that sign there is a convention based on our choice of flat space-time metric. And there are many books that use the opposite convention, so they won't have a negative sign there. So so keep that in mind. But in our mind, right, we know these are the components of the metric tensor, but that is a function of space-time. So if we ever take derivatives with respect to space-time, this is not a constant. That needs to be derivative needs to be taken there as well. So this is our length interval, our little length interval, and ultimately that's tied to what we want to minimize. So we would think that we are trying to minimize this functional S. We'll call it a functional S. I'm not going to call it the action, because we're really, and when I say minimize, that's even wrong. It's really extreme. We're trying to find the extreme value of this function. Sometimes it's minimizing, sometimes it's maximizing. But we're looking for the extreme value, those critical points of this object, right? So we're looking for functions x. Ultimately, we're looking for functions x of lambda, or x, all four functions x mu of lambda, such that when you stick those functions in here, you get an extreme value of this integral s, which the integral s is obviously the path length through space-time. So we're trying to minimize the path length. And I keep saying minimize because I keep thinking of the action principle, because you're always trying to minimize the action. But here we're actually trying to maximize the path lengths, right? It's going to be a maximal path length. But regardless, all we can hope to do with the Lagrange method is find an extremal path length and see that it makes sense. But we're trying to extremize this path length. And ultimately the answer are going to be these functions. The function, it's going to report back the coordinates with respect to the parameter lambda, and those coordinates, that's our answer. And as far as this so-called Lagrangian goes, I'll use the letter upright L, because it's not. I don't want you to really think literally in terms of the Lagrangian, the potential, the kinetic energy minus the potential energy. But our Lagrangian, our is going to be g alpha beta x dot alpha x dot beta, right? And that, remember, it's supposed to be a function of, oh, and I didn't mean to simply rewrite this. I meant to rewrite this with a little extra clarity. Mu is the metric is a function of space-time, and then we have, I better erase this, then we better have x dot alpha, x dot beta. What I'm suppressing is that x dot alpha is a function of the parameter, x dot beta, of course, well, that's the same thing, is a function of the parameter, x mu is a function of the parameter. So everything is ultimately a function of this parameter. So we suppress the function of the parameter nature of things, but I'm reintroducing the function of the metric as a function of spacetime. But just keep in mind, as we do our work, I'm always going to write the metric this way without the explicit indication of the function of spacetime. So if we express this in terms of how we were looking at normal Lagrangians, we say this is a function of x0, x1, x2, x3, x0 dot, x1 dot, x2 dot, and x3 dot lambda. Sometimes they like to put a semicolon because they don't want you to confuse lambda with these are the generalized coordinates, these are the generalized momenta, and lambda is the ultimate parameter, which is usually time in classical mechanics. So we're looking for 4 Euler equations, right? We're looking for 4 equations that are ultimately going to be traceable to this form: L x mu minus d by d lambda. Now notice the d by d lambda is not a partial derivative. It is a regular derivative. D by d lambda of partial L partial x mu dot equals 0. So there's 4 of these equations, right? One for each value of mu. One for each value of mu. Now it turns out they're all going to be essentially identical, so we can do it all in one fell swoop and just calculate it with x mu, and we'll get an expression, and it'll in principle be 4 different equations. But it is 4 different equations that we'll be generating in a moment. Now, one of the books that a lot of us use, or a lot of us have used, it's a really good book. It's written by DInverno. I just wrote down the spelling here. It's DInverno, not DInverno. DInverno. It's called Introducing Einstein's Relativity, and a lot of people that have been discussing these lectures have referred to that book. Probably I referred to it first. It's a book that I've been familiar with for a lot of years, and no book is perfect, but his book is pretty damn good. I really do like it a lot. One of the weird things he does is he deals with this equation. He attacks it in a slightly unusual way. That's because the book is so popular, and also because it isn't a crazy method. I mean, it makes perfect sense. We're going to mimic his technique in the book. If you have a copy of this book, which is not too hard to find, you'll find most of this work on page 99. We're going to duplicate it here anyway. But he wants to start by taking this equation and converting it into an equation involving L squared instead of L. And there are plenty of books out there that just take this Lagrangian, plug it into this Euler equation, and come up with the answer. He prefers to square this Lagrangian to sort of get rid of that square root, and then develop an equation, an equivalent Euler-Lagrange equation for L squared. So how does he do this? Well, he begins by multiplying this equation by 2L. Just like that. Just puts 2L out in front. So 2 times this thing which we are calling the Lagrangian. And then you make the obvious move, which I think actually is obvious, is that 2L times the partial derivative of L with respect to x mu is in fact the partial derivative of L squared with respect to x mu, right? If you took this derivative, you would get a 2L out in front, and then the chain rule would give you this piece right here. And then the 2L distributes right inside into this guy, where a lot of the action happens. So we jump ahead before we can go back, and we notice a fact about the derivative of, the derivative of this object if we replaced L by L squared. What would that look like? Well, we just execute it, right? D by d lambda of partial L squared partial x dot mu, right? That's not this, right? We're speculating what would this look like. And it's not too difficult to do, right? You just take the, you're going to just drive this right through. First of all, this we know, we've already calculated that. This inside is just 2L partial x mu from the straight up chain rule, and then this derivative here is acting on everything there, and then that just applies through the standard product rule, and we get the 2 comes out, of course, and you get the partial with respect to lambda of L multiplied by the second factor plus this first factor multiplied by this partial derivative with respect to lambda of the second factor. But the reason this is important is this guy right here looks exactly like that guy right there. And indeed, we're going to make that substitution by, we're going to flip everything around and solve for this guy. And voila, now we have an expression for 2L d by d lambda of partial L partial x dot mu, which is exactly the right side, or the right half, of the expression of our original Euler-Lagrange equation multiplied by 2L gives us this thing, which is just another restatement of the Euler-Lagrange equation. And now I can substitute this by this, ultimately giving us the answer. And this is the answer. This is basically the Euler-Lagrange equation in a slightly different form. That's all this is done. And DInverno likes to do this. I'm not absolutely sure why. I'm pretty I mean, clearly here and here things are made easier because L is now G mu nu x dot mu x dot nu, right? So there's no square root. So it's definitely true taking these derivatives will be a little easier. But you still got to do it here. You know, on this side, you still got to take, you know, it's not totally in terms of L squared. So, you know, I'm not quite sure. It's a bit of a wash. It's the only book I've seen that does this, but at the same time, it is a little easier. You just have to kind of work your way through all this stuff to get there. But once you're there, we can proceed, and we will in fact proceed from this equation, and finally and ultimately drive our answer that way. All right, so let's begin. So we are going to work with L squared being minus G alpha beta x dot alpha x dot beta. We know this is a function of spacetime. We know these guys are functions of lambda. L squared is a function of the generalized momentum x dot beta x dot alpha, and it's a function of spacetime through G, and ultimately it's a function of lambda through all of them being dependent on lambda. G is dependent on lambda through its argument, which is spacetime x, and say x sigma, and x sigma is a function of lambda. So everything's sort of a function of lambda. So let's begin this analysis. Let's do this piece by piece, looking first at this piece right here. We begin by just substituting in our function. Our function now is L squared, right? We're not going to take this apart the way you might normally take such a thing apart, which would be 2L and then partial L partial x mu. That's what we tried to escape. So we've almost renamed our function L squared. So this is the derivative of this object here, where this object here is L squared. And taking that derivative is very simple. We're treating all the generalized coordinates and all the generalized momenta as independent variables as far as derivatives go. That's why these are partial derivatives. It's holding everything else constant. So you're actually holding x dot constant and throughout this, but you're only changing x itself, and you're not changing lambda either. So the only thing here that's truly, strictly speaking, a function of x is the metric itself. So that ends up with our first. We're taking the derivative with respect to x mu, and it's an ordinary derivative, so it's a single line. And of course, in most treatments, you'll get a comma there, but we're going with a single line. So this would be alpha, beta, comma, mu. Or, I think, in fact, you would get partial, you would get this nabla mu g alpha beta. That's another way it's done. In fact, I'm pretty sure, I can't remember exactly, but I'm pretty sure that's how DInverno does it himself. Wait, no, they wouldn't do that. That would be the, that's not right. That would be the, if we did that, that would be the covariant derivative. But he might do something like this, right? Partial mu g alpha beta. All these things are the same, but this one here is my favorite, and that's the one we're going to use, where there's a little vertical line there. Okay, so that is the first term of our expression. Now we are going to calculate the second term. And for our first step, we just make the obvious substitution for L squared, and this is simply rewriting this expression by sort of isolating the derivatives we're about to take and the function that we're about to take them on. I was just making this substitution right there. And we just run the next derivative. We run the partial derivative with respect to the generalized momenta right in here, and we see there's the generalized momenta just sitting there. This is where we save a little trouble because we're doing it with L squared. If we weren't doing with L squared, there would have been this weird square root here, right? And to take that derivative, we would have ended up with 1 over the square root of the term here, and then we would be executing the derivative of the inside. So we've gotten rid of that part because we've converted our formula into this L squared. There may be some other reason to do this. I'm not sure what that other reason might be, but I'm pretty sure this kind of simplification is why we were after this conversion into this formula here. So we now execute this derivative. So this here is x alpha, not x mu. So we need the partial derivative of x alpha with respect to x mu and x beta with respect to x mu. G alpha beta, that's only a function of the generalized position. It's not a function of the generalized velocity. So it just is acting like a constant. So it's a very simple product rule here in this case. We could have pulled this outside all the way, for example. But this guy here is actually pretty easy to disentangle. That guy, that partial derivative, is going to be the delta function of alpha and mu. And this is going to be the delta function of beta and mu. In case you're wondering how that works, I just sort of sketched it out up here. The partial derivative of the generalized momenta, it's just this. You can think of it in terms of this relationship. It's the partial derivative. Partial derivative of alpha with respect to lambda, and the partial derivative of x mu with respect to lambda. You're really pulling this guy out front, and these two will end up canceling, giving you the partial derivative of x alpha over x mu, which is the delta function. So with those delta functions, we can simplify this and combine them, and that's what we'll do now, if I still have room. So let's go to red. This alpha will become now a mu, right? And this will go away. And then this beta, beta will become a mu also, like that. That goes away. And then we simply, then the next thing we do is we exploit the symmetry of G alpha mu and we'll write it as G mu alpha, right? And then we exploit the fact that alpha is a dummy variable, right? Alpha is a dummy variable. Beta here is also a dummy variable. So we can change alpha and beta at will. So we're going to change actually these betas. We're going to change these betas to alphas, right? Because they're in different terms, dummy variables, not repeated. They're repeated indices in different terms, so they're quite arbitrary. So anyway, we have minus G mu alpha x dot alpha minus G mu alpha x dot alpha, which equals minus 2G, that's a 2, right, not a partial derivative, 2G mu alpha x dot alpha. And that leaves us with this expression. In other words, the derivative with respect to the parameter lambda of this ultimately is that. And then we are headed on to our last piece of the evaluation, which is the evaluation of this guy with respect to lambda. So this is going to be a product rule application. We have two things in here which are functions of lambda. Everything, all of the generalized momentums are functions of lambda, and G is a function of lambda through its functional relationship to the generalized coordinates. So G mu alpha of x, say sigma of lambda, right? So it's a function of lambda through that. So ultimately we can expect an application of the chain rule here and then just a straight derivative here. So applying this through, working on the easy one first, which is the derivative of the generalized momenta, we just get a second derivative of the generalized momenta. Because remember, x dot alpha is defined as, well, it's defined as dx alpha d lambda. That's the definition of it. So x double dot alpha is going to be the second derivative of that, which is what we're ultimately finding here. So that guy, that's easy to figure out. The second one is now this derivative applies to the metric, and the second factor just comes along for the ride. And so the analysis of this in the metric is not too difficult. And here I've just drawn it in here. This derivative, the one we're seeking here, is an application of the chain rule. We know it's a function. We know G is a function of a space-time variable, which we're going to call x delta. So that derivative multiplied by the derivative of delta with lambda, which becomes this thing here. It becomes this ordinary derivative of the metric tensor component times the generalized momenta. And that is what we're going to substitute right into there. And we are ultimately left with this expression here. Right? This is the first part, and this is simplifying the second part. And remember, this whole thing, just to tie it back to what we were working on, is the evaluation of this expression, which is what we found is the second term in our new modified Euler-Lagrange equation. So we've written down our modified Euler-Lagrange equation. We calculated this first term on the left to be this guy here. We calculated this middle term, finally, to equal this expression here, which leaves us with the third term. Or the term on the right-hand side. So let's work on that one now. So here's that third term. It turns out we're only going to need to evaluate this piece. As I'm doing this, I'm maybe realizing why this simplification is helpful. So we only have to take an actual derivative of the original Lagrangian in one place. This one we'll see we can cleverly get around. But this guy we actually have to take its derivative. So what we're going to do is we're going to execute this derivative now using the original so-called Lagrangian, which is just that square root of minus G alpha beta x dot alpha x dot beta with the square root involved. That is, we're going after this guy right here. We can see what we're working with right here. we take this derivative of this expression and we get 1/2 times the what actually is L squared, right? Inside here is what we were calling L squared in the past, right? Or we are calling L squared, not even in the past. And then, of course, by the basic rules of differentiation, you get a minus 1/2 to that exponent. That's the step he seems to like to avoid by all of this. But now I'm actually beginning to see some of the logic, because the chain rule then has us taking the derivative of the inside, right? So it's the derivative actually with, I've used too many braces here, right? I mean, I haven't used two. This I'm going to change to braces, and then I have to close the brackets. So these brackets match up here, and these braces match up here, and these parentheses match up here. Just to be a little clear, you should never nest. Whenever you're doing work, you should never nest the same structure, right? In your, you should never have parentheses within parentheses. You should always alternate. And if you're going deeper than 3, you should really rethink your life, because that's there's some method you can use to escape 3 levels of depth in any expression. Anyway, so now we need to take this derivative. But you know what? Here's the thing that makes me suddenly appreciate DInverno's logic, which is we've already done this, right? We've already taken this derivative right here, right? And we learned, whoops, not there. We've taken the derivative right here, right? Is that the one we took? Yes. This derivative right here, right, the derivative with respect to the generalized momenta of L squared is exactly what's going on here, the derivative with respect to the generalized momenta of L squared. So we already know this. So I guess in that sense, we don't have to go through all of this retooling. We just know that we've got to get to this expression right here, minus 2 g mu alpha x alpha. So I should be able to write that right in there. That is, this whole thing equals minus 2 g mu eta x eta. I'm changing from alpha to eta. Remember, it's a dummy variable. I can give it any name I want, just because I don't want to collide with other uses of alpha later on that might pop up, for example, right here, right? So we'll just give it a new name, eta. So now we can clean this up. And this is what we get. All that break was this factor of 2 and that factor of 2. That negative sign comes out here, and we just sort of squeeze everything together. So this term here, which is the right-hand side of our Euler-Lagrange equation, right? That term, the right-hand side of the Euler-Lagrange equation, is equal to this expression here. So now we have to worry about this guy, right? We can't ignore that. And that analysis is actually goes back again to sort of the fundamental theorem of calculus issue. So let's quickly cover that. What we're understanding is that our path length in space-time as a function of lambda is from lambda 0 to lambda of L times these functional coordinates. So I'll just write it as x dot and omega d omega. That's the definition of this path length, where in the integrand we have the variable of integration is I've written as omega. But from the fundamental theorem, we know that ds d lambda, which is a function of lambda, which we will call s dot, which is a function of lambda, is, by the fundamental theorem of calculus, which we discussed in the last lecture, is this guy evaluated at lambda, is the integrand evaluated at lambda. And the s double dot is going to be, therefore, the derivative of L with respect to lambda, which is dl d lambda. So this path length, right, its first derivative is in fact this Lagrangian, and its second derivative is the derivative of this Lagrangian with respect to lambda, or And we can make this substitution right into our formula back here and write this as minus 2 s double dot, which is just a function, right, multiplied by all of this stuff here. Everything that was in this I can put right inside there like that. And so now I have gotten rid of this. I'm not worried about taking this derivative because I know that there's just a function out there that meets this requirement, right, whose derivative is this term. So essentially the path length itself, I'm taking it's a feature of the path length itself that just pops itself right up there. Now this guy here, this actually is L inside here. It's 1 over L, right? So this, this here, right, is 1 over L. But L is s to the first derivative, so it's 1 over s dot, right? So that actually can come out and give us minus 2 s double dot over s dot times g mu eta x dot eta. And so that is the expression. That expression ultimately, it's close to the end, but remember, it's only just a piece. This is not easy, right? This is a long calculation, but this here is what we're going to write this as. And we've evaded taking this derivative by understanding that this integral here through space-time, whatever our function is, however it's parameterized, this is that length through space-time, and the derivatives of it are all in the form of are all expressible through the quote-unquote Lagrangian through these derivatives, through the fundamental theorem of calculus. So now we take this piece, which is that, then we take this piece, which is this, and then we take this piece, which is this, and we add them all together. And that's our next step. All right, so here's our Euler-Lagrange equation in slightly modified form, and now we'll substitute for the first piece. And there's the first piece. The first piece is the easiest one, right? That was just a simple partial derivative. Now we will substitute for the second piece, which I'll do in green, I guess. And this is our second substitution here. This is where the second derivative with respect to the parameter pops in. Another partial derivative of the metric with respect to space-time, and the generalized momenta pop in again. And that takes care of this, and that takes care of the entire left-hand side. And now the right-hand side, which I'll do in blue, right? The right-hand side will be in blue. And voila, there we have it. This is essentially this is our equation of motion, right? This is our equation of motion based on that Lagrangian that we've defined in the beginning, or in terms of this Lagrangian L squared. Now, however, this can be heavily simplified, and we shall now do that in order to, ultimately this has to look like the geodesic equation we learned from our mathematical treatment, right? That's what we're trying to show. Notice, by the way, the connection has never entered into this problem. That's an important point to make. There's no notion of gamma, alpha, beta, sigma, right? Or whatever indices we give it. We don't know anything about the connection on the space-time. We do know the metric, right? We do know the metric because that's part of our physics. We believe that, we're still dealing with a four-dimensional manifold that has some metric, g, alpha, beta out there. But this hasn't been bundled together in any kind of connection. So we still have to make contact with all of that stuff. So how do we do that? Well, we do that because we kind of know the answer, and we're going to just do algebraic operations from this point on that get us to that show us essentially we need to prove that this mess right here is the same as our classic geodesic equation. So we're just going to do algebraic manipulations to prove that's the case. So we'll start by realizing, well, here's our second derivative of the space-time coordinates, and we know that exists in our geodesic equation. It's always on the far left. So let's rearrange this so we collect everything, at least put it in kind of that order. So we're going to move this to the far left. And that's what we've done here. So I've now moved this term over here, and now we're going to take a close look at this. I haven't bothered to rewrite this term on the right-hand side. So now we're going to take a close look at this guy. I want to take x dot alpha beta. I know that in the final geodesic equation, those the two generalized momenta show up in the second term. So presumably I should be able to pull these guys out. Well, the good news here is that delta is a dummy index. So if I change delta to beta, or let's say I change beta to delta, then I'll have an x dot alpha, x dot delta, x dot alpha, x dot delta, and I can pull that out. So let's do that. And here we've done that. We've simply pulled it out front, and I've left behind the minus and the plus inside the brackets. Now, this is our next step to have a close look at and to manipulate and control. We are now in a full-fledged mode of we are going to turn this thing into the connection, because here we have the this term here, which I should copy and paste into here. This term here, clearly we're beginning to see, okay, there's the second derivative term. Here's the product of the two first derivative terms. So this thing here, if we could make this into the connection, then we would have something getting close. We still have a problem with the with these metrics out there, and so what are we going to do next? So we're going to manipulate this guy. And the next manipulation is not too difficult. I take this 2 and I pull it out here, which means I have to incorporate a 1/2 on the first term, and then what's left behind I split up into 2 1/2s. So notice the indexes here are identical to the indexes there. I've just gone 1/2 and 1/2. And so now this is beginning to kind of look like the connection. I mean, I know where this is going. If you're following this and saying, "Oh man, I never would have thought of that," believe me, neither would I. Right? I didn't invent this, but I have worked through it plenty of times, and so it feels very familiar. So I talk about it as, oh, look at this obvious thing, but none of this is obvious, right? We're trying to make this look like something we already know the answer to. The point is you want to see that you can get there. All of these things connect. And we're trying to show that this physical argument is going to connect to our mathematical argument. And it's going to do so through the metric connection, right? Ultimately, this is going to be the metric connection. But I split this up into 2 pieces. But the good news is it's symmetrical out here. Alpha and delta are really sort of the same object. So I can flip alpha and delta here. And you'll notice if I flip alpha with delta, I'm still summing over the same guys over here. So it really doesn't change anything. It's kind of a clever observation. But alpha and delta are totally symmetric here. And so if I flip it here, it sums to be the same sum. If you executed the sum, you would get the same number. So I'm going to make that flip, right? I'm going to make that flip. And a little bit of other simplifications in our next step. Let me move this up a bit. Whoops! I just noticed something. When I changed this delta, or when I changed this beta to delta, so I could pull out this term, I changed the beta here, but I didn't change it in the index down here. So this beta should be a delta. It's following me around because you got to change both of them, right? You got to change both of them. So this has to be alpha, I'm putting it in green to make the alpha delta mu, right? Likewise down here, this has got to be alpha delta mu. Right, you understand the idea is I wanted to, this is a dummy index, beta, and beta's dummy. I want to change it to delta so I can pull out alpha delta in front. So I changed that to delta and pulled that in front, but I forgot to change that one. So it's alpha delta mu, alpha delta mu. I'll leave that in green just to highlight the slight error. But notice now I'm still going to work on swapping alpha and delta here, and I do that this way, move that like that, and I've done the swap in red. And here you see, all I swapped is delta and alpha, and it seems like, well, wait a minute, you can't just swap delta and alpha and expect this term to be the same, and that's correct, except that ultimately the reason I can do that is these are dummy variables in a term separated from these other terms. Alpha and delta are here, alpha and delta here. So I could, if I switched, well, it's not because they're dummy variables, right? Because if they were just dummy variables and I took delta and switched it to alpha, then I would have two alphas. So I'd have to switch that to gamma, and then I would have gammas, and that would just be a mess. That doesn't get me anywhere. But the fact that I can switch them, and this term over here are the same. This is symmetric. Switching delta to alpha and alpha to delta, and then if I reverse these two, which they're commutative, I get the same sum. So the point is it's the same sum. So this guy here is now my internal expression for, or the expression for what, these are derivatives of the metric, So I'm going to take that combination of derivatives and use my definition of the metric connection to substitute for the metric connection. And this is that definition of the metric connection. That nu is that's ridiculously big, isn't it? But that's the definition of the metric connection. And look, what we're very close to having it, right? All these terms are correct. If I put the two positive terms up front, pull out the 1/2, I get the 1/2. I'm missing this. I'm missing the inverse metric tensor. But that's good, because I'm just going to multiply through by g mu nu, right straight through the whole thing. And what will happen is this will end up being, this g mu nu over g mu alpha will give me a delta function. When I multiply it in this term, I will get the metric connection exactly, times a factor of 2. And when I multiply it on the far right-hand side, I will get g mu nu with g mu eta, and that will give me a delta function over there. So this is looking pretty good. So I'm going to multiply this expression by g mu nu. Let's see if I have the room to do that here. So first I'll just move the definition of the oops. I'll move the definition of the connection out here to the bottom, and then I will duplicate this expression here like this, and let me move it a little further to the right, and then I will separate this a little bit to give me some room, and let's see if I can do it now. So here is, this is g mu nu multiplied straight through. This ultimately here will give me the delta function nu alpha. This times this will give me the connection coefficient, and I think the subscripts are going to be alpha and beta. Let me quickly check. No, the subscripts are going to be delta and alpha. Delta and alpha. Delta and alpha. Delta, alpha. So all that's going to put that there. And this is going to give me delta nu eta. Okay, so now I can make those index substitutions, meaning now everywhere I see an alpha I can put a nu. I can make this substitution right away. And here, everywhere I see an eta, I can put a nu. So I will now rewrite the whole expression with that in mind. Move up again. So here I actually forgot a 2 when I moved this piece from up here, right? There's a 2 there, right? That's important too because it's got to cancel, right? We don't have a 2 in the final result. But if you put in these delta functions, you get the second derivative of the generalized coordinate with the new index. You have this new index connection coefficient. You have the new index on this side, and then you have all these 2's, which I guess can be all canceled out. And you're ultimately left with this thing, which is our geodesic equation. It's not equal to 0, though, but it is still the geodesic equation because it would express a displacement where the direction of the tangent vectors is the same direction as the tangent vector of the curve. The parallel displacement of the tangent vectors is equal to the new tangent vector, just a different magnitude. However, remember we dealt with this question of the path length, right? This path length was calculated. S is the path length, right? So if we have our curve, S really is the amount of path lengths between any 2 points on that curve, right? That distance is S. And that's a parameter we like. We like our curves in general relativity to be parameterized by the length of the curve itself. So if you did that, if you said that lambda will equal S, right, then S dot is equal to 1, and S double dot is equal to 0, and this whole side goes away, right? And you do get your 0. And that's the whole point. This thing shows you a couple of really amazing things. First of all, it generates the connection coefficient. The connection coefficient it's instructed. It gives us the metric connection because all we gave it was the metric, and it comes back with what we've mathematically decided was the metric connection. So the physical argument gives us the metric connection, and it also tells us, hey, if you parameterize the curve with the path length, you get a nice simple equation. You get this whole thing equals 0. Okay, so that is the easy way, in a sense. It starts with in our case, manipulating the Euler-Lagrange equation a little bit. And that was purely, you saw, that was purely a way of just attacking the mathematics of the problem, right? The actual Euler-Lagrange equation is always and always will be this thing right here, inside, not with the 2L, this part right here. And but we found this mathematical manipulation of the Euler-Lagrange equation, and we used the standard path length integral as the function to extremize, and the Lagrangian L is still this creature right here. We just squared it in order to facilitate using this version of the equation here. We still needed it, by the way, right here. We couldn't get away from it. But I guess that's the motivation. Then we understood that the path length eliminated this term using the fundamental theorem of calculus like we did before, and ultimately we end up with our same geodesic equation. It teaches us not only how to parameterize it to get a nice simple expression, but it also gave us the actual metric connection itself. Now, the dirty little secret of this whole thing is that there are paths in space-time for which this expression right here is always 0. Right? If you're a light ray, this is 0 along your entire path. And so that's a big problem. So our next lesson, we're going to talk about a slight modification of the Lagrangian to get that path length, to allow for conditions where that path length is 0. It's a little bit of an obscure point, but it's not always covered in books. In fact, DInverno sort of ditches the question himself. But I will do sort of an optional lesson on how to do this analysis for null curves also. Okay, see you next time.